Hello all, a warm regards to you all. This is Lydia Christie, working as an assistant professor in the Department of Biomedical Engineering, Hindustan College of Engineering and Technology, Coimbatore. In the domain of biomedical engineering, there are various imaging modalities. Today, we will discuss on ultrasound imaging, which is also called as sonography. The learning objectives of today's session are understanding the basic principles of ultrasound, identify the components of an ultrasound machine, and describe the clinical applications of ultrasound. To begin with, let us understand what ultrasound refers to. Ultrasound refers to sound waves with higher frequencies which are above the human audible range. The human audible range is from 20 to 20,000 Hz. So any sound waves above 20,000 Hz are referred to as ultrasound. In real world, dolphins use ultrasound to see underwater using high frequency sound waves. In the context of biomedical engineering, let us understand what is ultrasound. So ultrasound imaging is also called as sonography. It is based on the principle of pulse echo principle, using high frequency sound waves to create the images of the internal body structures. Ultrasound helps in visualizing the internal body structures using high frequency waves. The sound waves frequency ranges are from 2 MHz to 15 MHz. Let's now understand the principle of ultrasound. When a high frequency ultrasound wave is sent into the body, the wave travels through various tissues and partially it gets reflected at the boundaries between different tissues. The reflected echoes are detected by the transducer and then processed to form an image. This is the basic principle under ultrasound imaging. Components of an ultrasound machine. When you visualize an ultrasound machine, you can see a display monitor, a control panel with different knobs, an image storage system and different transducers, and a central processing unit and the power supply. There are different types of probes used in ultrasound imaging. So, let us discuss what are the different types of probes available for imaging in an ultrasound machine. The first probe used is a linear array probe. The frequency range of this probe is from 5 to 15 MHz. It has a flat surface and it helps in visualizing musculoskeletal systems. Then we have a curved array probe, which is also called as a convex probe, which has a frequency range of 2 to 7.5 MHz. The shape of this probe is a curved surface. It helps in visualizing the abdominal regions. It is used in gynecology. It is used to visualize the pelvis and also obstetrics. Then we have a probe called the phased array probe. The frequency range of this probe is from 1.1 to 5 MHz. It has a very small footprint and it helps in visualizing the cardiac structures. Then we have the endocavity probe. The endocavity probe has a frequency range of 5 to 9 MHz. It is very curved and slim. It helps in visualizing the regions which has a cavity, like the transvaginal region, the transrectal region, or pelvic examinations. Then we have a microconvex probe which has a frequency range of 5 to 8 MHz. It has a shape which is curved and which is very small. It helps in visualizing pediatrics, neonatal brains, and also the abdomen. Then we have 3D and 4D probes, which uses a frequency of 2 to 7 MHz. It helps in visualizing the real-time 3D fetal imaging and also it is used in gynecological application. Working of an ultrasound machine. Okay, so the first thing is the generation of ultrasound waves. The piezoelectric crystal which are placed in the transducer, it will convert the electrical energy given into the transducer into high frequency sound waves. The range of this high frequency sound waves are from 2 to 15 MHz. These waves are transmitted into the body. Then The propagation of wave occurs through the tissues. The sound waves travel at different speed depending on the density and elasticity of the tissue. For example, soft tissues, the speed of sound is 1540 meter per second. For bone, it is 4080 meter per second, and for air, it is 3030 meter per second. After the propagation, the reflection and the echo formation happens. When ultrasound waves encounter boundaries between two tissues with different acoustic impedance, then a part of the wave is reflected back as echoes, and a part continues. The reflected echoes are received by the same transducer. And finally, the image construction. The time delay between the transmission and the echo reception determines the depth of the structure. The intensity of the echo determines the brightness, the grayscale of the image. The system creates a real-time two-dimensional image based on the reflection. There are different modes in ultrasound. The first one is A mode. A mode plots echoes as a function of depth, where x-axis is the depth and y-axis is the amplitude. This is widely used in ophthalmologic applications. Then we have the 2D or B mode. This is the standard method of scanning. The spatial oriented structures are seen as a function of brightness. Depth and width provides a cross-sectional view of the underlying structures. All the anatomical structures can be visualized using this B mode. Then we have an M mode, which helps in visualizing the cardiac valves and fetal heart rate measurement. It takes a small section of the horizontal beam and displays it over time. Then we have the color Doppler. This color Doppler uses Doppler shift and helps in visualizing the blood flow and velocity. Then we have the power